Here we are back again for the second part of Unit 1 on radian and degree measure. Let's just recap what we did in the first session that we had. We worked with standard position, made that clear what that was. It's in standard position, the vertex is at the origin. The initial ray is always the positive x-axis, and the terminal ray is what actually shows the angle. We learned how to measure angles in degrees or radians, and we know that 180 degrees, or a semicircle, is equal to pi radians, still a semicircle. We reminded ourselves of some of these definitions from back in geometry, including what a central angle is. That's, of course, in a circle. It's called a central angle because its vertex is at the center of the circle. So a central angle is located with its vertex here and has as its rays the radius of the circle. We learned how to find the arc length, but we didn't actually practice any of that. What did we find? That the arc length is equal to the angle expressed only in radians, correct? Times the radius. It's very important that this measure has to be expressed in radians. Today we're going to work some more with this, plus we're going to go back to talking about measuring angles in degrees, because there's more we need to know about degrees than what we first learned in earlier courses. And this is what it is: the degree, minute, second system. In every degree, here's 1 degree, there are 60 minutes. In every minute, there are 60 seconds. Doesn't this sound familiar? It ought to be pretty easy to remember because it's exactly the same terminology and subdivisions that we use when we're talking about time. And when we think about an analog clock, it goes around 360 degrees. So there's 360 degrees in a full revolution, and each degree, well, it doesn't actually work out just right, does it? But we could say there are 60 minutes in a full revolution, and there are 60 seconds in a minute. So it doesn't hold up entirely. If we want to convert this to degree, minute, second, the DMS system, how would we go about doing it? Well, we know that this is the portion that's going to be expressed as minutes and seconds. It's some portion of a degree. The whole for a degree is right there. We know we've got 37 degrees. Now, how many minutes are there in 0.425? 0.425 degrees. Well, if we multiply this times 60, we will know how many minutes we have. Let's pull over our calculator. See if I can operate it here. Turn it on. We'll put in 0.425. We'll multiply that times 60. So that equals 25.5 minutes. So here's the integer value we're going to use for minutes, 25 minutes. Then we've got 0.5, or half of a minute. Half of a minute will be how many seconds? Of course. Now here's a little question for you. 1 degree will have how many seconds in it? We know it's got 60 minutes in it. And if we multiply that times the number of seconds in each minute, we get our answer. So the answer here would be 3,600. Adds up fast, doesn't it? So we just converted decimal degrees to the DMS system. Suppose we're given something in the DMS system and we want to convert it to decimal degrees. Well, we know that we've got 42 as our integer. 24 minutes is equal to how many degrees? If we divide 24 by 60, we'll have our answer. So let's pull up our calculator. 24, it's going to be something less than 1, isn't it? Better turn it on. 24 divided by 60. Okay, so it's 0.4. It turned out to be even, so you don't have to worry about going any further. Oh, yes, I do. Because all I did was take care of this. I still haven't taken care of 36 seconds. How many degrees is that? Okay, we're going to take 36 and we're going to divide it by the number of seconds that are in a single degree. We'll pull up our calculator. I'm sure you can actually do this one in your head, but we'll just prove it to you here. 36 divided by 3,600 equals 100th. So we need to add 0.4, that's the 24 minutes, 4/10, plus 0.01, 100th, that's this one. We put those all together and we get our answer of 42.41 degrees. So we can go either way. The thing you have to keep in mind is what is the relationship between minutes and degrees, seconds and minutes, or seconds and degrees. Now you can actually do this on your calculator. So let me see if I remember how to do it on your calculator. Okay. There is something called the DMS function on your calculator. We can look in angle. Let's see if we can find angle. Something called angle here. Oh yes, here it is. It's a second function just above that blue apps key. How do you get to that? Do you know how you get to your second function? Second on apps. It should give us angle. It does. This is great. By the way, I just learned this. I never knew this was here until I was reading Stu Schwartz's workbook. And there it is. If you want to convert something to DMS? You can. Oh, I have to, my calculator, I have to go down like this. If I wanted to convert what I just had here, 0.01, to DMS, we know what that's going to be, right? Whoops. It's going to be 36 seconds. Let's do this whole thing. So we're going to first type in the decimal version. Then we're going to go second function to get to angle. We're going to go down to number 4, select that, and then hit return, or enter rather, and we get just what we expected to get. Suppose we've got something in the degree, minute, second system. I'm trying to get this up out of the way for us so we can see what we're doing. We want to convert this to decimal degrees. All right, we have to use, let's see, we find degree in angle and minutes in angle, but to get to the double quote, we have to use the alpha key and the plus key. Let's see. Here's our alpha key. It's this turquoise one. Plus key, of course, we know. And you see over here in blue? Okay. So first, we have to type it in the degree, minute, second system. Let's try this. Actually, it's the first time I'm doing it. So we're going to say 42. Second function to get to angle, and then we're going to put in the first one, degree. Then we're going to say 24. And we're going to go back to second function, angle. We're going to go down 1 to minute, hit enter. And finally, 36. This one we're not going to find an angle. We're going to use our alpha key and go over here to, where's my plus key? Right here. Okay, enter. So there's a way to use your calculator to get these answers that we just did by hand. Let's try converting some. I want to look ahead a little bit here so you can be planning your time. We've got an exercise we're going to do. You can do that on your own and then check back to see that your answers match. Then we're going to do something with arc length, and we'll do a couple more examples. And finally, I'm going to do another problem that I like very much that did not come out of your workbook. When you see a slide that has the blue background, that's right in your workbook, so you can do your work right in the workbook. We've done this, now we're going to do these. 23 degrees, 30 minutes. I don't think we need a calculator for this, do we? 30 minutes is half of a degree, so decimal would be 23.5 degrees. How about this one? Oh, I might need my calculator for this. Whoa. Okay, so for B, I'm going to, I mean, of course I could figure this out mathematically without using this special function, but I think it's just fun to use it, so let's try it on. I'm going to put in 141 degrees. Oh, I didn't mean to do that. I'll try it again. I don't even know what I did. 141. I must have hit something twice. One of you can tell me what I did. Enter. And then we're going to put in 25 45, then we'll use our alpha key, seconds. Hit enter and it'll give it to us in decimal. We knew it would be 141. 141. How should we round that? Just say 0.43 perhaps? 0.43 degrees. For this one, what is 0.25? That's 1/4, isn't it? 1/4 of 60 is what? I'm going to have 12 degrees. And 1/4 of 60, I mean, just think about a clock, right? Quarter after the hour, how many minutes is that? 15 minutes. This next one we're not going to be able to do quite that easily, are we? We know it's going to be 39 degrees, but how many minutes is that going to be? We could probably estimate it, couldn't we? It's a good idea to estimate, actually. That way you can know whether or not your answer makes sense. We'll put in the decimal degrees, 39.426. We'll go to second function angle and DMS. Hit enter to figure out what it is. So we end up with decimal seconds. That's kind of messy. All right, 39, 25, 33.6. 39, 25 minutes, 33.6 seconds. All right. This is an interesting one. How far away is this from 60 degrees? 1 second. So close. If we were rounding, of course, we would be putting in 60. 60. So what do we expect to get for decimal? 59.999 or something like that. Let's see. 59 degrees. 59 minutes. And 59, I'm going to use my alpha key now. Whoop, over here. And I hit my enter, and it will tell me what it is in decimal degrees. Ooh, I was pretty close. 59.9997. I'll put that whole thing down. That's good. 59.9997. Okay, here's a little challenge for you. Can you spot the goof? It's coming up. And this one, it's just the tiniest bit away from being a perfect 127 degrees. So let's put that in. 127.001. Second function in angle. DMS. Hit return. And there it is. It's 127 degrees, 0 minutes, and 3.6 seconds. 127 degrees, 0 minutes, and 3.6 minutes. And you do have to put the 0 minutes in there. We're going to talk about circular arc length. Before we do, I just want to speak a moment about how we name our angles. We can use alpha, a Greek letter, beta, we love Greek letters in mathematics, gamma, theta, which we've already talked about, phi, and omega. So any of these may show up. I usually use theta. We already talked about this formula. We know the arc length is going to equal the radius times whatever the angle is in radians. So let's try some examples. These are right out of your workbook, so you can go ahead and do them and then check back later to see if you got the right answer. Find the arc length of the arc with a radius of 4. Okay, so we're going to use the formula that we have learned here. Makes sense. This is in degrees, theta. We want to know what it is in radians. 60 is 1/3 of 180, so it's 1/3 of pi. That's what we have to use for our calculation. If you don't use radians, you will get the wrong answer. But it'll be conspicuously the wrong answer. You'll look at it and you'll ask yourself, does it make sense? And you'll say, it doesn't make any sense. If my circle only has a radius of 4 inches, how could an angle of 60 degrees give me such a long arc length? Pi over 3. So our arc length is 4/3 pi. Now that's I should have inches, shouldn't I? Inches. That's a perfectly acceptable answer to me. I like it. It's exact. However, if you're actually talking with somebody other than a mathematician, they might like to see this in decimals. So let's pull this over and we'll figure out what it is in decimal. 4 times pi divided by 3. For instance, if you're talking to a carpenter and you gave this, they'd say, what are you talking about? Come on. So we want to say, let's say 4.19 inches. 4.19 inches. And we ask ourselves, does that make sense? Yeah, that makes sense. The radius was 4. This looks like it might be a little more than 1 radian or 1 radius. So 4.19. If the arc length is 6 and the radius is 2, find the central angle in degrees. It's tricky because this formula is going to give you the central angle in radians. We're going to have to work through this. So the arc length is 6. The radius is 2. What is the central angle? Well, it must be 3, and that's anytime you're working with this formula, that's radians. 3 radians is equal to how many degrees? Well, we could think about it a moment. We know it's going to be almost 180, isn't it? What's our conversion that we use? We know 180 degrees is equal to pi. pi is equal to 3.1416. 180 degrees. So that's a little more than 3. How do we get there? Well, you could set up a little proportion, right? 180 is 2 pi as, we're going to say x degrees is to 3 radians. We could solve that. We get x equals 3 times 180 divided by pi. Let's get this into degrees. Let me pull up the calculator for us. We'll say, turn the calculator on, 3 times 180 divided by, where's my pi? Right there. Equals 171.9 degrees. When we ask ourselves, does that make sense? Yes, because we knew with 3 radians we'd be over here getting close to 180. If the arc length is 2 meters and the central angle is 120, find the radius. Okay, so central angle 120 is 2/3 of 180, so it's 2/3 pi. So we've got a 2. I have to be careful because my 2's sometimes look like they are z's. Oh my goodness. So it's the radius times 2 pi over r. That's the central angle in radians. So r is equal to 2 times 3 divided by 2 pi. 2 over 2, of course, is the same as 1. So this is all equal to 3 divided by pi. Let's pull up our calculator so we can get a decimal answer, something that maybe makes sense to us. Get rid of this. Turn it on. 3 divided by pi. So the radius is 0.9, come on, what was that? 0.955, we'll say. 5. And what are we talking about? Meters. Does that make sense to us? 2 meters, if the radius is almost 1, 2 meters would pretty much take us over to around 120, wouldn't it? Here's another example. Assume the Earth is a perfect sphere and its radius is 4,000 miles. Close enough. Miami is at this latitude. Erie, Pennsylvania is at this latitude. And the cities are on the same meridian. Okay, so we could slice this right in half along this meridian, and we would see this arc length. Find the distance between the cities. It's not a straight line because we have curvature of the Earth. The Earth is not flat. So we've got a radius of 4,000 miles. Of course, this is as the bird flies, right? Distance between cities, we typically measure it according to a roadway system. But anyway, so what is our central angle? That's going to be tricky to figure out, isn't it? We want to know what S is. And our central angle is actually given to us here, but it's kind of hard to figure out at the moment. It's all in degrees. We know we're going to have to convert it, but let's work with degrees for a moment. If we find the difference between these two latitudes, that will be our central angle. So we've got 42 degrees, 7 minutes, 15 seconds. And we're going to subtract from that 25 degrees, 47 minutes, and 15 seconds. Well, thank goodness for that. So that will zero out. In order for me to subtract 47 minutes from 7 minutes, I have got to convert this from 42 to 41 and use that other degree over here. I'll make this 67 minutes. Hope this is making sense. Subtract them. And now, how many degrees do I have? That makes sense. If I add these all together, will I get what I've got above? Yes, okay. Now this isn't really useful. I would like to have this in decimal degrees. Let me pull up my calculator. It's so easy to do it on the calculator. Seems like we ought to use the tools that we've got on 16 degrees, 20 minutes equal, we could have figured that out. We know that 20 minutes is 1/3, right? So now we cannot put degrees into our formula. We're going to use this formula. We have to know what this is in radians. So what is 16.3? In radians? Well, 16.3 is degrees. We've got 180. Whoops. 180 in pi. We've got the same relationship over here. We want to find, this will give our angles in degrees. Let's bring up our calculator again. So we're going to say pi turn it on. Pi divided by 180 degrees times 16.333333, I'll put a lot in, degrees. So theta, when I do it in radians, is 0.285. So it's fairly small. We expected that, didn't we? That pretty much makes sense. So now I can say the distance between these cities is 4,000 times 0.285. And of course, we're talking miles. Let me just multiply this times 4,000. We'll round it to the nearest mile. 1,140 equals 1,000, make that a comma, 140 miles. There it is. Okay. Circular arc length. Oh, I love this problem. Okay. The running lanes at Emery Sears Track, let's get this right, are 1 meter wide. So if we look at the inside diameter of each of these, we'll see that the inside track has a radius of 33 meters. The outside track has a radius of 34 meters. How much longer is lane 2 than lane 1 around one turn? That matters, doesn't it? I mean, especially in a close race. Okay, so let's see how much longer it is. We know that we're going to measure the inside of each of these lanes. So the arc length for lane 1 is going to be, let's see, this is lane 1. It's a radius of 33. And what do we know about the angle? It's a semicircle. It's 180 degrees. We can't use degrees, but we can use radians. We know it's pi radians. And the arc length for the second track so that's pretty easy to see. The difference is 1 pi, and what's our unit of measure? Meters. Now, if you were talking to the track designer, I don't think you'd want to tell them pi meters. You would say 3.14 meters. So whoever gets lane 2 actually has to run. That's significant, isn't it? 3.14 meters longer, further than whoever gets lane 1. That doesn't seem fair. What could be done to equalize the distances run? Well, if lane 1 starts right here, that's their starting line, maybe we could move this one up just a little over 3 meters for their start, and that would equalize it. That ends it for our second section. When you come into class, our next class, you'll be doing the homework problems number 2 and number 3. Of course, we will discuss any questions that have arisen in this section. See you soon.